So, good morning. So today we're going to be expanding on what we talked about in the last week with respect to material balances, and now we're going to be doing material balances not on one process, right, with just a couple in and out streams, but now we're going to have an interconnected system, which basically means that the descriptions that we're going to have of how the process is built is going to be a little bit more dependent on recognizing a couple of key terms. What's a reactor? What's a separator? What's a mixer? What's a splitter? Right? And how many streams you would be expected to draw in and out of those systems. So I'm going to draw out a arbitrary process where we can have one stream entering, and I'm just going to call it unit 1. There could be a stream coming out the top, a stream going over here. We could have a stream coming midway through, and this could go into unit 2. And this needs some outlet streams. So now we have a process with multiple unit operations, right? Each one of these boxes is going to be a unit operation. It could be heat exchanger, all sorts of different other things, you know, all the stuff I listed already. Distillation column, flash separator, reactor. How many different balances can we do on this process? So if we're going to do a mass balance, like what we did last week on the distillation column, right? We just had that one unit operation, the distillation column. And we counted all the mass streams in and all the mass streams out. How many can we do on this system? So I heard 3. What do we got?
3. 1 around unit 1, 1 around unit 2, and 1 total.
Okay. Does anyone else see any other balances we could do? There's also a 4th one right here, which is the mixer. So we could have 1 here. We could have 1 here. We could have 1 here. And someone correctly identified we can have 1 going across the entire boundary. So we can have here a total of 4 balances. That's pretty standard. Now, you could also maybe think of another balance where you looped in unit 1 and the mixer as well. That could be balances. You could have another balance here. So in theory, there's a lot of different possible ways that we could write a balance. Now, when we're doing a material balance on a system, all we're keeping track of is the streams coming in and streams coming out. Because I guarantee you that a distillation column in a real chemical plant is going to have more than just 1 stream in and 2 streams out. Right? But we're magically drawing a line around just those overall pipes that are going in and out of the system. Right? So what we're doing when we're doing a material balance is we draw a box around some part of our unit process, and we're keeping track of only the streams that cross through the boundary, because those are the only ones that we care about. Right? So in general, we typically would do each unit operation as their own balance and then a total, but there may be a situation where you can cleverly draw other balances looping around different parts of the process as well. So when we're working on a system with multiple balances, we need to start with the balance, each of these 4 balances here, that result in 0 degrees of freedom. Right? We may not necessarily be able to solve unit 2 before we solve unit 1 or before we solve the mixer. So depending on what pieces of information were provided, it's not going to be crystal clear what is the balance to do. So you might write out a ton of work and realize, oh, I can't solve any of these equations. Right? It's not going to be wasted work because eventually you will go through and use all those balances. But in this case here, if this is a, let's say, 3-component system, right? A 3-component system with 12 balances results in, 4 balances. Let's see about this. That results in 12 independent energy balance equations you can write. 1 for every species in the system, and you can do that balance over 4 different sort of unit processes. Right? So you may end up writing a ton of equations down before you realize, oh, number 11, that's the equation that I can actually solve. But then once you solve that, then maybe you can solve the next, and you can solve the next, and so on and so forth. In general, you'll be able to have a better idea than just total random chance choosing an equation, right, by looking at the processes. And that's what the degrees of freedom is supposed to be for. Now there's a couple of specific terms for multiple units, especially when it comes to reactors. And if you've looked at your homework, you'll have seen at least one of these equations. There's a very, very common type of unit operation called a reactor separator. But before we get to that, let me just draw out two definitions here. This unit operation that we see here is called recycle, where we take some of the outlet of a process and loop it back. Now there's another unit operation. Now imagine that this recycle line doesn't exist here, called bypass. So recycle is when you flow through a system and then you send some of it back through around. Bypass is where you take some of the stream and you skip it and go back through. So these are two definitions that are important to know. Now these unit operations here, a mixer or a splitter, in this case here you can have either a mixer or a splitter, these are kind of called like simple unit operations, right? There's no change in composition as you go through them. Right? So if we had a mixer or a splitter, these are simple and no composition change is what makes them simple. Just imagine it's kind of like a valve where you're sending some down one stream and some down another stream. Right, so you're not changing your composition, but you're changing your overall flow rates. That's what's happening at a mixer or a, well, so rather. So wait, hold on, this is a bit confusing. So a splitter will have no composition change here. But a mixer may have composition change because you could be mixing two different streams of two different compositions. Right, but there's no reactions, there's no separations going on. So yeah, so that was a confusing way to put that. So a splitter, no composition change. A mixer, it's still a simple unit because there's no fancy separations going on the inside. So one of the most common unit operations that we're going to see in this class is a reactor separator. Let me write this out big so that everyone has a... And we're going to be spending a lot of time working with the reactor separators as soon as we start doing chemical reactions. So this is a reactor separator. In it we have a mixer, a reactor, a separator, and a splitter. This line coming out here is typically called the purge stream. Over here is the feed, and this is the recycle. So a reactor separator is a unit operation that is used when you have a chemical reaction that only goes very slightly forward. Right? So if you have a reaction that's really hard to accomplish, you might only get 1%, 2%, 3%, 5% conversion through a single pass of the reactor, which basically means if we have 10% conversion, that means 90% of all of that stuff that we're buying, right, to do this reaction is going to be wasted. So what happens is you send in your feed, it goes through the reactor, only some of it reacts. So what you do is you have a separator that's designed to pull away, typically your product comes out of the bottom stream, and send back your unreacted materials back through a mixer and through the reactor again. Right? So the amount of material that's cycling through this process can be many times bigger than the feed. The recycle ratio is the ratio of the recycle to the feed. Is N of recycle divided by N of feed. Now the reason why typically you have the product coming out of the bottom is because in general with chemical engineering, we want to take cheap, readily available, that typically means simple chemicals, and turn them into something bigger and more complex. Now a bigger, more complex molecule is easier to condense into a liquid phase or crystallize out into a solid, which means it's typically going to be coming out of the bottom of any unit operation separator, whereas the cheap, readily available, simple molecules are more likely to be in the gas phase, which is why they would come out of the top and be recycled back through around. But that's the general rule. It's not always going to be the case. But in general, the goal is to make bigger, heavier, complex molecules at a rate that is cheaper and more efficient than anyone else can make bigger, heavier molecules. Right, so these are unit operations with multiple individual processes. But basically, everything from here on out is exactly the same as what we've done before. The only difficulty is, right, your solution for one unit operation is going to be dependent on another, and then another, and then another, right, and it goes through in a big circle. And so breaking into it sometimes typically involves first looking at an overall balance and then kind of working your way through individually. So we're going to go through an example now. Are there any questions on terminology or where we're going with this? Yeah?
Sorry, why would you have a purge right there?
Ah, very good question. So a really good example of why you need a purge is anytime you work with air, for example. Right? So in the Haber process, it's you make ammonia out of nitrogen in the air plus hydrogen gas. So air is not just oxygen and nitrogen. There are inerts in the system as well. So for example, argon in the atmosphere is a very small fraction of it. But what happens is if we didn't have a purge stream here, we were to get rid of this, and we were to do an overall material balance. If we had a feed that consisted of air, right, and then maybe that comes with a little CO2, it comes with a little argon, but the product out of here, and hydrogen, right, because this is potentially the Haber process, if the product here was, let's say, ammonia, we would have an accumulation of other gases in the system, namely the inerts. CO2, argon, anything else that's not reacting. In this case, the oxygen could also be considered an inert. So what happens is if we don't have a purge stream and we do the individual species balances, we'll notice that we'd have an accumulation term. And so the concentration of argon in the reactor as a function of time would just continue to increase. And it would be displacing, volume of the reactor that could be used for effective chemicals. So you have to throw some material away in a purge. Yes?
So like in the separator, as you just keep changing the temperature, so you get it to a temperature that separate the argon and open the purge stream? Or like, what is this?
No, so the purge stream is continuously flowing. So you just have to throw some material away just to prevent accumulation. And so in general, with all of these strategies, they're always going to be steady state and continuous, so you wouldn't be modifying any part in this process as time went on. You would want to keep it at whatever you've calculated to be the ideal scenario, right? And this is exactly what you're going to be going over in your senior year in the senior design class. So in this class, we're more or less going to keep it pretty simple, right? I'll tell you what the temperature of the separator is. We'll make it clear what one variable you're solving for. But when you're in your senior design class, the senior design class is going to say, okay, should I have a bigger reactor to make sure that I have a greater recycle ratio and get a higher overall conversion? Is it worth going from a 90% overall conversion to a 95% overall conversion if it means my reactor has to be 4 times as big? Should I operate my separator at cryogenic temperatures? Should I operate it at ambient conditions? What kind of separator should I use? These are the design considerations that you'll be going over in your senior design class. Right now, we're just kind of looking at the big picture overall, but a lot of the subtle details about what temperature, what kind of catalyst, what type of a reactor, should I use stages in a distillation column versus a continuous packing? All of these very subtle decisions will come down in more of a senior design class, because you'll have to learn how the inner workings of every single one of these unit operations happen in the junior year classes. Right? Heat transfers for designing heat exchangers, reactor designs for designing reactors, separations is for separations, mass transfer, you need to know that to do separations and everything like that. Then of course fluid mechanics is everything we're working with is fluid. Right? So right now we're big picture. Next year you'll zoom in microscopically to figure out how the science of every single one of these processes work, and then senior year you zoom back out again and say, I'm going to take everything I know now and try and figure out how to get everything to work. Oh, did you bump it?
Yeah.
No problem. And just tilt it back. Yeah, looks reasonable. Okay, so on to an example. And we'll work through a multiple unit balance. Okay, so in this example, we are separating a dirty air stream. So we're cleaning up a dirty air stream with the air is contaminated with acetone and water. So we're mostly concerned with getting the acetone out of the air because we have to inject it somewhere else. We're going to be injecting it to the atmosphere, so we need to make sure that there is no volatile organic chemicals. So this is an adsorber column. It's a unit operation that is intended to strip contaminants from an airstream. There are other types of unit operations where you strip contaminants from a liquid stream. That's called a stripping column. So if we have a gas feed coming in here, and I'm going to call this 1, we're going to assume a basis of 1,000 kilograms per hour. The gas feed is, in this case, let me draw out, A is equal to air, AC is acetone, and W is water. Just to save me some time writing everyone out. This stream here is 95% air, 3% acetone, and 2% water. Coming down the top, we have a pure water stream. Coming out here, we're going to say we have a pure air stream. This is a simplified scenario. In the other bottom stream of the adsorber column, it is 19% acetone and 81% water. That will go into a distillation column. Where we're separating a fairly highly concentrated acetone stream, and coming out of the bottom, we have the remainder. So just 2 unit operations. I'm going to label the streams 1, 2, 3, 4, and this same one here is 4, so I don't label it again, but I can write here as a reminder, 5 and 6. Okay. How many different balances can we do? or how many unit operations can we do a balance over? So we've got the absorber is 1, distillation column 2, and overall balance 3. Let's write out our unknowns. So fortunately in this problem, the composition of every stream has been defined. The feed to the process, the stream connecting it, and the 2 product streams coming out. And these 2 here are pure streams as well. Now in the future, we know that it's going to be difficult for us to get pure air coming out of the top, so we'll have some impurities, some water evaporated. But for this example, we're oversimplifying and saying it's just pure coming out of the top and just pure water coming into the bottom. So our unknowns. We have M1 is fully defined, so we don't know M2, we don't know M3, we don't know M4, we don't know M5, and we don't know M6. So we have 6 total unknowns. Oh, 5 unknowns. Where should we start?
Let's start with the water balance and the distillation column.
So we have a suggestion to start with the distillation column. Let's just quickly do an overall material balance on the distillation column, right? This is a continuous steady state process, right? So that means in is equal to out. That is our balance. That's our default assumption unless otherwise stated. So coming into the system, we have M4, coming out we have M5, coming out we have M6. How many degrees of freedom do we have under that circumstance?
3.
Technically 2, because we have that one equation with the 3 unknowns. So we need to have how many more equations to solve that system? 2 more. Can we get 2 more equations on the distillation column?
Yeah.
Can we? What are the 2 equations we can get in addition?
Acetone balance.
Acetone balance and water balance. But we started off with the total balance, right? So we have 3 unknowns, 4, 5, and 6 flow rates, but we only have 2 independent balances, right? The acetone balance or the water balance. So unfortunately, we cannot solve the distillation column yet. Now let's try another one. Let's try a total balance. All right, let's walk through the total balance in our heads. We have M1, 2, and 1 and 2 entering, leaving we have 3, 5, and 6. Well, that's a lot of unknowns, isn't it? Right, so the unknowns we have, let's see, water, air, bottom stream, and top stream. That's 4 unknowns. But in this case, we actually are closer than we think, though, right? Because we have 3 species in these balances. We have acetone, air, and water. But again, we have 4 unknowns, but with 3 independent material balances. So what does that leave us with?
Acetone.
Balance is on the absorber column. Right, so if you look at the absorber column, we know everything about stream 1. Stream 2, we have unknown 1, unknown 2, unknown 3. So we have 3 unknowns if we do a balance on the absorber column. But how many independent species do we have? 3. Air, acetone, and water. Okay, so we've determined we're going to start off with the balances on the absorber. We've done our degrees of freedom analysis already. How many unknowns do we have? We have 3 unknowns and 3 balances. That gives us 0 degrees of freedom. Now we could write out how many different possible balances. The answer is 4. Right? We could write out an acetone balance, we could write out an air balance, we could write out a water balance, and we can write out a total balance. I don't want to write out all the balances. Which one should we start with?
Air's, we don't really care about air because we know all the air is leaving, right?
In general, it depends what kind of question we're asking. Here, we're looking to balance the whole process. So we will care about what is the air flow rate of the system. But I think air is a very good starting point. Now, why is air a good starting point for this one? Right. It's only involved in 2 streams, right? There's nothing in streams 2 and 4 with air. Stream 1 is fully defined. So in our heads, we know that if we write out the air balance, we should just get one unknown equation, right? So we're going to write out the air balance. I'm just going to write it as A balance. Again, this is in equals out. So coming into the system, we have 1,000 kilograms per hour. Now the composition of this stream, right, because right now this is 1,000 anything kilograms, right? The units need to be kilograms of air per hour because we're doing an air balance. And so our units of our composition is 95 kilograms of air per kilogram. Oh, sorry, per 100 kilograms. Right? Or you could write this as 0.95 over 1, but it's equivalent, right? Well, let's do that. That's a better way to do it. I like that better. 0.95 kilograms. 0.95 kilograms of air per kilogram of feed. Okay, that's everything coming in, and coming out of the system, we can just have m dot 3 because m dot 3 is 100% air. And if we wanted to be meticulous with our units, we could say that for every 1, you get 1 kilogram of air per 1 kilogram of flow rate of stream 3. If we want to be meticulous with our units, right? So the answer here should be 950 kilograms for flow rate of stream 3. What now? What should we do now?
Isn't it kilograms per hour?
Oh yes, kilograms per hour. What now? What one should we do now?
Acetone?
Acetone. Why acetone? Let's break this down just so we can think through every step. Why acetone?
It's completely defined. Yeah.
Again, same thing with the air, right? The acetone is actually only involved in 2 streams. So again, since stream 1 is fully defined, stream 4, it would make a lot of sense that we should be able to get one equation and one unknown. Water, on the other hand, we have 1, 2, 3 sources of water with 1, 2 unknown flow rates. So that means we're going to have a degree of freedom if we're trying to do the water balance. So let's do the acetone balance then. AC bal. Okay, so same thing here. It is in equals out. This is an open steady state process coming into the system. We have again 1,000 kilograms per hour. And we have 0.03 kilograms of acetone per kilogram of feed. Leaving the system, we have an unknown flow rate, mass 4. And its composition is 19% acetone, so 0.19 kilograms of acetone per kilogram of feed. Is there any questions on how I got that material balance? Right, this is an acetone balance, so our units should be in mass or moles of acetone. In this case, everything's on a mass basis. So we have the total flow rate of the stream times by its composition. This will give us kilograms of acetone per hour. This is equal to our unknown mass flow rate, which is going to have units of kilograms per hour, times by kilograms of acetone per kilogram of the feed. This is all the acetone entering, and this is all the acetone leaving. And from here, we will get our m dot 4 is equal to, I've done the math out, 157.9. 157.9 kilograms. All right, so we are 2/3 of our way done. And this is m dot 2. What now? Do you want to do a water balance, or is there an easier way?
Should we do the distillation column?
Total absorber column?
I say, yeah, do a total balance on the absorber column. Because then I don't have to deal with all these units of concentration. It's just more stuff to write out. Right, so I'm just going to do the total balance then. So So if I do the total balance, it's just N equals out again, but I don't have to worry about all this concentration stuff. So I have 1,000 kilograms in, plus what else is going into the system? The water, right? I don't know that one. M dot 2. Leaving the system, we have 3 and 4, which we have here. M dot 3 plus M dot 4. We have these numbers here and there, and so we can solve for M2. M dot 2 is equal to, I have it written down, 107.9 kilograms per hour. But there's multiple ways we could have solved this, right? We could have done a water balance. There's nothing to stop us at all, right? So the question is, well, in our heads, well, in my head, I figured it was easier to not have to deal with the concentrations. But I have more terms here, right? I have 1, 2, 3, 4 contributions to my total balance. But if I were to do a water balance, I would only have 1, 2, 3. But if I wanted to be really diligent with my units, I'd have to write out the concentration change and the composition changes. So it's not crystal clear which is the best way to solve the problem. And as things get more complicated, there's going to be a lot more ambiguity about the order of operations and how you solve the different steps. Okay? All right, what now? What should we do now?
Well, using all the information we have on stream 4, it's now easier to find the distillation column.
Exactly. So we have two options, right, though. So we could do the distillation column or we could do the total balance. Which one do we want to do? Distillation. So if we did the total balance, we could do the total balance, but then we're kind of introducing all this air that we don't really care about, right? We might as well just focus in on this column here because we still have the two unknowns. And we have two independent balances, which is the acetone and water balance. Now, if we did the total balance, we're in the same situation, but we've got a lot more streams to worry about. So it makes more sense just to zoom in and do the distillation column itself. But again, it's not like you couldn't solve the problem by doing a total balance. Right? This is just a subjective judgment call of what we think the most efficient way to solve the problem is. So now let's look on the distillation column. How should we solve it? What's first? What's our first step?
Acetone.
Why acetone? Why not water? Does it matter?
No, but we
That's
had
what
to
we
figure
care
out.
about normally, right?
Well, it depends. In this particular instance, we care about balancing everything out. But if it were about, because again, water, again, typically is not the one we care the most about. You're right. The organic compound is probably the one that we're paying for to either clean up or pay to sell or whatever the case is. But let's think about it mathematically just for a second. Do we know any more information about the acetone than we do the water? No. So those are going to be pretty similar equations. Do you think we're going to be able to get this down as simple as one equation and one unknown? Because let's do the balance really quickly in our head. Right? Coming in, we have everything defined. Right? We have the total flow rate and the composition of this stream. Coming out, I don't know the total flow rate, and I don't know the total flow rate. So if I did an acetone balance or a water balance, I'm going to have an unknown mass 5 and an unknown mass 6 no matter what. So if I were to do this by hand, I know I'm going to get a system of two equations and two unknowns, no matter what. I do the water balance, I have M5 and M6 in my equation. I do the acetone balance, I have M6 and M5 in my equation. So typically, if I'm going to do substitution by hand, I would much rather prefer to do one species balance and then one total balance, if I were to do it by hand on an exam. Now, if I were to do it using a computer tool, I'd actually prefer to do two species balances because then the equations are equivalent in structure, right? And so what I want to spend now in the distillation column is we're going to have sort of two divergent approaches. If I'm doing it by hand, how do you solve a system of two equations by hand? Substitution. At least that's the way that I know best. Right? You can also add and subtract equations, but I don't remember that stuff very well, right? I do substitution when I solve equations by hand. When I solve equations on a computer, I want everything to look as similar as possible so I don't make any mistakes. So I'm going to show this example here as if we're doing two species balances. But note that if you were to solve it by substitution, I would prefer to do it out using a different format. Okay, so let's look at our acetone balance. Coming into the system, we have our m.4, m.4, and I'm going to truncate the units here just to make things go a little bit more smoothly. 0.19 is the composition of our acetone for the inlet stream. Leaving, we have m.5 times by its composition, which is 0.04. And leaving out of the top, we have m.6 times by 0.99. Right, so we have two equations, so one equation with two unknowns. Right, we know M4 because we had solved for it previously right there, 157.9. Now we do our water balance, and we get a similar equation, but just with slightly different numbers. 0.81 coming in. Coming out, we have mass flow rate 5 times by 0.96. 6 times 0.01. So let's talk about some strategies here. Let's name, so we talked about one strategy already, which was substitution. What's another strategy that we can use to solve a system of equations? Now note these are a system of linear equations, so that opens a lot of tools up to us. What are some tools that you guys talked about in your linear algebra, or maybe back into high school, your algebra 2 type classes?
Yeah, matrices.
What was that?
Matrix.
So we can do matrix math. What else do you think of? I know reduced row echelon form, right? That's another strategy. That's what I'll use a lot of times if it's a simple equation. So let's talk now a little bit about strategies. So if we wanted to put this into a matrix, I would structure the matrix in this form. AX equals B. We have our coefficient matrix, we have our unknown matrix, and we have our solution matrix. Right? So if we wanted to put our acetone balance and our water balance into matrix form, we have to just do a little bit of rearranging here. So we need to pull out our unknowns and put them into the X matrix. So this would be m.5, m.6 equals our solution matrix. I'm going to call this the acetone equation is on the front top row, and the water equation is on the second row. So we just need to restructure this. 0.04, 0.99. I believe that's right. I didn't make any mistakes. Nope, that's right. 0.96. And then over here we have 0.19 M4. Who feels comfortable solving this equation? Who doesn't feel comfortable solving this equation? There's some iffies. So let's talk about a couple of examples here. So we can solve, if this we call matrix A, this we call matrix X, and this we call matrix B. In MATLAB, we can use X, so this is for MATLAB. X is equal to A/B. That'll give you the right answer. You could also do RREF of A, comma, B. These are some functions that we can use to solve this. Again, this is not a math class, right? I don't need you to solve this by hand. It's helpful to know how MATLAB solves these things, right? But we don't have time for that. That's really what your numerical methods course is for, or your linear algebra course is for, right? In this class, I just want you to be able to solve the problem, right? You don't need to know how the sausage is made to solve the solution here, as long as you know how to use a tool and solve the problem. So with these strategies, eventually we can come up with a solution. And we have m.5 is equal to 133.0 kilograms per hour, and m6 is 24.9 kilograms per hour. How does everyone feel about this? Now, typically, we're not going to be seeing much more than systems of two equations of two unknowns. Now, it's possible you could find 3 equations and 3 unknowns, and to some extent, it depends how you want to solve the problem. So you could take an approach where you basically write out all the material balances and just say, you know what, I don't want to think about this. I'm just going to throw it all into the nonlinear solver, and I'm just going to let the computer work it out. And that's a totally fine solution, right? The only problem is you might run into some issues on an exam if you want to try and apply the same strategy. We didn't have to solve this individually and sequentially. We could have solved 5 equations and 5 unknowns like that, right from the start, right? These are all linear expressions. It's all adding and subtracting numbers. There's no multiplying and dividing involved of 2 variables. So in theory, we could have solved this entire system just by writing out 5 independent material balances, writing it into a big 5 by 5 matrix, and solving it. Now, if that seems easier, go ahead and do it. For an exam, it might make things a bit more difficult because I would say writing out a 5 by 5 matrix and getting all the math to line up well is a bit on the trickier side, right? Just logistically making sure you don't flip 2 things here or change 2 coefficients there. And for an exam, it's going to be a lot easier if you can solve one balance, then the next balance, then the next balance, then the next balance. Okay, any questions on solving multiple processes? And then with the last few minutes, I was going to go through a really quick demonstration of Excel. Because I typically think that Excel is, you don't need much more complex than Excel to solve most of the problems in this class. Now, if you're dealing with a system of non-linear equations, which we will be dealing with, in those instances, you're going to have to rely on a computer tool. You're not going to be able to solve them by hand. You'll have to use some sort of a numerical method to get to that solution. Okay. So I've actually programmed up this this exact example into Excel. You can see it up there. I'm hoping to get it on this main screen here when the projector powers up. Let's see. Yep, it's thinking about it. So a couple of things that won't be on the video, but you guys can see over here. I have a very...
You can just tilt it.
Yeah, I feel like it's best not to mess with that. We can just wait a second for it to power up too. But I have a particular way that I like to format my spreadsheets. Here we go. Yeah, it doesn't do a very good job with the gain either, though, unfortunately, so it might be hard to see regardless. I'll post this onto Canvas. I think it already is on Canvas, actually, too. If you go into Class Examples under the Files folder. A couple of things. Now, up here, I have a legend of sorts, right, where I am defining how to view the different cells. One thing that you'll very quickly find, either in this class or general sort of technical programming class, is that most of your time is never spent solving the problem. Most of your time is spent troubleshooting, right? Because the ability to write hundreds of lines of code without an error is extremely hard to do. So a little extra time formatting spreadsheets will make it so that you can actually troubleshoot your code in a reasonable time frame. So this is why I do it this way. And then for MATLAB, if I write in MATLAB, I be sure I comment everything and I try and break it into sub-blocks so that I can troubleshoot one sub-block that does a particular action. Now, the reason why I do it this way, I have an input cell, a calculated cell, and a constant. Now, every single one of those cells I know requires a certain troubleshooting task. So it takes away an element of my thought process for me to get to that right solution, right? So on an input cell, all I have to do is, did I put in the right number? Right? It's as simple as that. I know that every input cell, I can just change the number. Every calculated cell, right? Like for example, this one here, and you can kind of see it, but it's grayed out. Now in my personal spreadsheets, I use colors to differentiate between the different ones here, but for printing it out for demonstration purposes, this is the black and white version, so I kind of reformatted it. Now when it comes to a calculated sheet, I have a formula. So every time I see a calculated cell, when I troubleshoot it, I know, did I type the formula in right? Right? I don't have to worry about numbers or anything like that. So I never, under any circumstances except for one, put numbers in a calculated cell. It's always in reference to a different cell. Now the one circumstance that I do violate that rule is for unit conversions, because there's not really a good way around it. Unless you want to have a cell for the unit conversion ratio, which maybe some people would like to do that. I typically don't, because that's a step I don't usually make an error on. So when I'm building these spreadsheets, and this is, I promise you, in my day-to-day life, I do this as well. This is not just for teaching demonstrations. So since most of your time is spent troubleshooting, I want to make sure that I break it into small compartments. Is this a number that I copied down wrong? Is this an equation that I entered in incorrectly? And when you format it this way, you can scan through the spreadsheet really quickly and know where did I go wrong, right? But if you've got a super long equation with numbers and a million parentheses, it's going to be really difficult for you to check both the numbers and that you've entered in your formula correctly or incorrectly. And so if we look at this input cell here, this is for mass flow rate of stream 2. And in this case here, it's a total balance, which is exactly what we did for the water, right? It's the in, so I have in minus out, So I solved for stream 2, but if you were to work out D7, E7, and B7, it corresponds to the total flow rate of 1, 3, and 4. 1, 3, and 4, and so you can see that I just typed that into there. And so if I change my basis to like 500, right, everything should automatically update except for one, which is these two columns right here, right, because these are input cells. Now I have an input cell set up, oops, don't mess that up. I have an input cell set up for streams 5 and 6, right? I could have in theory done all the substitution and solved this out, but instead I'm using Excel's solver to help come through and solve this problem here. And so the reason why I formatted them as input cells is because we've got two equations and two unknowns, right? These are the solutions here. Every computer solver is a guess and check system. So instead of me inputting the number, Excel is inputting the number and then varying it continuously until it comes up with the right answer. Now how I set this up is, let me go to the board here real quick. In Excel, when I solve a problem, right, in this case I have an unknown x1 and an unknown x2, and these are in equation 1 and equation 2. Right? I have two equations, two unknowns. Now, let's say, for example, this is linear. So I have y1 equals mx1 plus b. y2 is equal to mx2 plus b. Right? It's the same exact problem that we're dealing with, right? Two equations, two unknowns. I don't know m and I don't know b. How I enter the equations into Excel is I say 0 is equal to y1 minus mx1 minus b. 0 is equal to y2 minus mx2 minus b. Now I haven't changed the equations at all, right? I just moved the left-hand side to the right-hand side or vice versa. But what it allows me to do is it allows me to check my cells right here and I say, are those 0? I'd say 10 to the minus 6 and 10 to the minus 7 are pretty close to 0. But if I were to enter those cells in with an actual number for y1 and an actual number for y2, I would have to go, oh, okay, equation 1 is equal to 17. Now is 17 the number for y1? Oh, equation 2 is 42. Now is 42 for y1. This way, I just look at it and I say, did I solve my equation? Oh, it's 0. Yeah, I solved the equation. So if I were to scale the basis again, and let's say we're doing this 500, right? Oh, I need to resolve my problem because these aren't equal to 0. So it's a little extra step, but it saves me a lot of mental time and effort, double checking numbers, comparing things, and that's all wasted time. Right? So whenever you're using a computer, make sure you let the computer do what it's good at and let you focus on what you're good at. I know with certainty that a computer is better at comparing two numbers than I am. So I'm never going to compare two numbers on a computer. The computer is going to compare two numbers. What is easy for me, I only have to compare one number. Is it 0 or is it not 0? And so structuring it this way makes it a lot easier. So for those of you who don't know how to use solver, there's goal seek. Goal seek is only good for one equation and one unknown, but it could be nonlinear. You need solver for two equations and two unknowns. Oops, no, not right there. Tools, so let's see. Oh, I don't think I have solver set up on this one yet. No, I've done this before. Where is it? Oh, I know what it is. This is, I upgraded to the 2017 version of Mac Office, and I haven't installed the solver yet. Okay, well, if you don't know how to use solver, come talk to me after class or in office hours. I don't think you need it for this lecture, for this homework, but we'll talk about strategies and how you use solver. It's just the mechanics of it, but yeah, I forgot that I didn't install it. Okay, anyway, have a good week, and see you on Wednesday.